Hello class. So this is the second video in section 5.2. In the previous one, we saw how to find net area, meaning that now if we have a function that is not always positive, but it can be above or below the x-axis like we have in this picture. Well, what's the net area? Well, you add the area above the x-axis, right, and then bounded by f, and you subtract the area that's below the x-axis and bounded by f. And for approximation wise, we saw that it's the same formula that we use for approximating area when the function is always positive. It's the same thing. In this example, we did a left Riemann approximation, right? So your function value is always given by the left endpoint. Right? If the function value is negative, well, there's a negative that shows up, and all that means is that our triangle is below the x-axis. So we're taking the negative of the area. So in doing this, we're already approximating net area because when the function is negative, we're taking the negative of the area, right? And we're adding that, so that negative shows up. So we're finding net area. Right? Whatever's above the x-axis is positive. Whatever is below the x-axis is negative. And again, based on how we do it, we just do the same algorithm. It's always the same. Okay. So there's nothing new there other than seeing graphically what's going on and understanding that when the area is above the x-axis, you add the positive of it. When the area is below the x-axis, you add the negative of it. Again, even though the area is positive by definition, if it's below the x-axis, you add the negative of it. Okay. So that's what net area was. Right? So computed the same way. Graphically, it looks like this. Now, we want to stop doing approximations or let me not say stop doing approximations. We want to get our approximations to be as accurate as possible. Now, as we saw in the first couple of videos in section 5.1, we did a couple of examples where we approximated area using 2, 4, and 8 subintervals. We saw that the more subintervals we used, the better the approximation was. So we're going to, in theory, what would be net area then? Well, in theory, we would use infinitely many rectangles. Of course, in practice, that's not possible, at least with the techniques we have, right? We can't draw infinitely many rectangles. But at least theoretically, this is how we're going to define net area. So if you remember this formula here, this part where we thought the limit as n approaches infinity, so it should be n here. So let me rewrite this. So what I wrote is net area. We're going to define it as the limit as n approaches infinity of the sum k equals 1 to n. Remember, this is a sigma sum. Change it next. And if you remember, when we were doing the examples with sigma sum notation, this n, this part here meant that we had n subintervals. We were picking an x value in each subinterval. It was either the left endpoint, the midpoint, or the right endpoint, right? Evaluated the function. This was giving us the height of the rectangle, right? The function evaluated, and this was the length. And again, n was the number of subintervals. Okay. So how do we use infinitely many subintervals? Well, take the limit as n approaches infinity. Right? N is the number of subintervals. We want infinitely many so that we can have a better approximation. Well, then take the limit as n approaches infinity. So that's all this definition is saying. We're going to take the net area to be the limit as n approaches infinity, or the limit of this approximation, which is saying we want to approximate the area with infinitely many subintervals. Okay. Now, this is just theoretical for a lot of reasons. First, again, how do we take a sum of infinitely many rectangles, of areas of infinitely many rectangles? We don't know how to do that. So that's the first roadblock. This is why it's theoretical. Second, this is a limit. As we know, limits might not exist. So I see two roadblocks. How do we take a sum of infinitely many terms? I don't know, right? And then what if this limit doesn't even exist? Then what's going on? Okay. So logically, this definition makes sense, right? We want n to be growing to infinity because n is the number of subintervals. So we just take this limit as n approaches infinity. But again, in practice, what are we doing? Now, thankfully, we have one answer to one of those roadblocks. So remember the two roadblocks where does the limit even exist? Right, because it's a limit, we know it might not exist. The second roadblock was, how do we compute a sum with infinitely number of terms? And so how do we add infinitely many areas of rectangles? Well, thankfully, there's an easy answer, which I'm not going to prove. Okay, it's not easy. It's going to be easy for us because we're not going to prove it. But there's an easy answer to question 1. And that's our first theorem. As long as the function, and I keep making this mistake, this should always be n. As long as this function that we're using, so the function that's bounding the area, as long as that function is continuous, this limit is always going to exist, always. Now, of course, we're not going to prove it, right? Because it's hard to prove. But this limit is going to exist as long as your function is continuous. Now here, I also talked that the function can be bounded with finite number of discontinuities. Don't worry about that part, right? All the examples we're going to be worked with are where f is continuous. So that's more for, if you go to higher level maths and then you start taking these courses called analysis, you'll see more of that. For our purposes, all that matters is if our function is continuous on the interval, this limit, whatever it is, we don't know how to compute it yet, because to do it, we have to take infinitely many sums, right? So we don't know how to compute it, but it exists. So that's the note here. Right, so that's what this theorem is saying. Now, the theorem is saying a little bit more. It's saying that, so this other part, this next paragraph says that, okay, so that limit always exists. Good. That's the part we're really interested in. Not only that, it's unique and independent of what value of x of k we choose in each subinterval. Right? So what is this saying? Well, as we saw in the previous examples, and we even did one in the previous video, we choose a value of x in each subinterval. Right? We either, for our purposes, we've always been choosing either the left endpoint, the midpoint, or the right endpoint of each subinterval to evaluate the function there. What this theorem is saying is it doesn't matter. So another thing this theorem is saying is it doesn't matter what x value you evaluate in each subinterval. It could be the left endpoint, the right endpoint, the midpoint, any point inside the interval. It doesn't matter which one you choose to evaluate your function value at, this limit is always going to be the same. Now, I'm not going to write that down because for us, theoretically, it's good theoretically, but for us in practice, it won't really matter other than knowing, okay, it doesn't matter if I take a left endpoint, midpoint, or right endpoint approximation. I'm always going to get the same value for this limit. Okay? So that's all it means for us. Now, again, in higher level math courses, this is more relevant. It might be easier to compute, to compute this sum when the x value is taken to be something clever, right? So maybe not the left endpoint, midpoint, or right endpoint, but for something else. But for our purposes, it doesn't matter. Right? Again, what's important is if your function is continuous, this limit exists, and it doesn't matter if we use a left endpoint, midpoint, or right endpoint approximation. It is always going to be the same value when we take the limit. Right? So if you remember, we did examples before where the left Riemann, midpoint Riemann, and right Riemann sums were different, right? But we were using finitely many subintervals. What this is saying is when we take the limit, when we take infinitely many subintervals, we always get the same answer. So just think of it that way. When we start seeing how to evaluate this sum, it doesn't matter which endpoint you choose or midpoint, you're always going to get the same answer. So I understand this is theoretical. That's why I'm trying to focus on this is what you have to be careful. This is what matters. And that's why I started that thing here, like that thing there. Okay. Now, so that answers one problem. Okay, this limit exists whenever the function is continuous. Now, of course, we still don't know how to evaluate it, right? But for now, let's skip that a little bit and just introduce notation. Now we're going to introduce the definite integral. Right? Now you're going to see why this notation makes sense. So a function f satisfying theorem 1, so for us this means f is continuous, on AB is called integrable, right? Just meaning that the integral exists. And what's the integral? Well, the integral is just going to be the net area. Okay. So what does this notation mean? All it's saying is, instead of writing the limit as n approaches infinity of the sum k equals 1 to n of f of x of k dx, instead of writing all that, we're going to shorthand the notation with this. So the integral sign, which as we saw before, kind of looks like an elongated S. Now we want to have all the information here. So we're trying to get the area, the net area of the interval a to b, of the region bounded by the function. Okay, so we put that information here. That's just for us to remember that the interval goes from a to b. Then the function, right? So that kind of matches what's going on here, right? So the function, so we know what is it that's bounding the area, and then the change in x, we just write it as dx. And now it makes a little bit more sense where this notation comes from. So kind of think of it as this part as getting all of this information, including the interval. Then of course the function value, well, that's there. And oh, this was changing x here. And then this last part, the x, well, that's just the length of each subinterval. So that's where this notation comes from. Now, of course, this is called a definite integral, and notice that it means something different than the indefinite integral. This definite integral, by definition, this is the net area. That's what it means by definition, right? This, remember, this was net area. So this definite integral just means the net area bounded by f on the x-axis on the interval a to b. So we use the same notation, almost the same notation as for the indefinite integral, but it's not the same, right? For an indefinite integral, we did something similar, but we didn't write the interval. So it's different. This is an indefinite integral. So we don't write, so the difference notation-wise is for the indefinite integral, we don't write the bounds of the interval. For the definite integral, we do write the bounds of the integral. So that's the difference in notation. And of course, it means a different thing. This means all antiderivatives of f on some interval. On some interval I. Now, we're using the same notation. Right? So that means these have to be related. Somehow, net area has to be related to antiderivatives. We're not there yet, but this is what we call the fundamental theorem of calculus. That's the relation between an indefinite integral, or the antiderivatives of a function, and finding the net area bounded by a function in the x-axis. So again, we still won't get there, right? That's I think in section 5.4. So we still won't get into what the relationship is exactly, but for us, we can see there's a relation because the symbols are almost the same. Right? So we'll get to that, but right now for us, just remember this notation here is just a shorthand for writing the net area. Instead of writing that whole limit of that approximation sum, just write this notation.